Okay, so today we're gonna spend some more time talking more about the physiology of bone. Last time was mostly anatomy and microanatomy of bone, so we'll get into a little bit more about the function and how bones work today. So let's start out with this clicker question here. Go ahead and talk to the people on your team there and vote when you're ready.
You don't really know which bones it are.
There's something to do with
All right, go ahead and send it in if you haven't yet. We got most of you, it looks like. Okay, so about 3/4 of you are saying B, and then the other quarter saying A. So yeah, most of you are saying false. All bones do not have growth plates, which that's the correct answer. Okay, not all bones have growth plates or epiphyseal plates. There's two types of methods of the way that bones develop. Okay, and the bone development is called ossification. Okay, so there's two types. There's one called endochondral, which just means within cartilage, right? Chondro, endo, within cartilage. Okay, that's the one we're going to dive into some details here in a sec. But then there's another type of ossification called intramembranous, which just means inside of a membrane. And that's kind of how our flat bones, irregular bones, those types of bones, that's how those develop. And there's no growth plate involved with that type of ossification. But we won't really go into detail on that intramembranous one, but we will go into detail on endochondral here in a sec. So give you a second to finish writing that down. All right, looks like most of you are done writing there. So yeah, we're going to dive into that first one there, the endochondral ossification process. Okay, so here it is. This is just a lot of words here on this slide, right? Kind of explaining the whole process, broken up into 4 big steps. Okay, so what we're going to do, this is kind of an opportunity to practice in the way that I recommend you studying for process-based things for this class, which is kind of read it over in the notes, read it a bunch of times, try to kind of study it, memorize it. And then I'm going to have you kind of work through it with these pictures here, putting these in the right order, kind of trying to understand what's happening in each one, and then writing it out in some version of your own words, but using the correct terminology, which is really how I recommend you studying for processes in this class anyways. And that doesn't mean just like the exact same words from this slide get transferred onto the other slide. That doesn't really help you much, okay? But if you can kind of try to interpret what's going on and kind of explain that in your own words in the 4 steps, but then again putting in the correct terminology, I think that's a great way to study for these process-based things and get you ready for those hybrid questions for the exam. So that's what I'll have you do in a sec. But let me just kind of talk you through a little bit of it here first. Okay, so that first word there, it's a type of cell, right? What type of cell do you think it is? Cartilage of some sort. And then the blast, what do the blasts do? I'll blast a bunch of stuff out. That's what I picture right there. Sending a bunch of proteins out, right? They're making the cartilage stuff, okay? So we got chondroblasts in the perichondrium, Okay, it's another big word we haven't seen yet, but perichondrium is the membrane, kind of just like the periosteum, right? The periosteum is the outside of bone, right? That external membrane. This is the membrane on the outside of cartilage. Okay, so same idea, right? And that's a lot of times where we have a lot of those cells is in that membrane part. Okay, so on the outside of our cartilage bones, we have cells that are going to differentiate into osteoblasts, right? So those chondroblasts actually turn into osteoblasts instead, right? They kind of transition from being cells that are making cartilage to cells that are making bone. Okay, and then again, that there's that same word about the membrane on the outside of cartilage that gets converted into a bone membrane instead, periosteum, right? So that's kind of the first step. Okay, because we're starting with fully cartilage bones. That's what the fetal skeleton is just all hyaline cartilage, right? And then we're going to convert those bones into, or those cartilage bones into actual bones. And so this is kind of taking you through that process, right? So first of all, we switch over the pericardium to, or sorry, the perichondrium to the periosteum, and some of those cartilage cells turn into bone cells. Okay, and this all happens due to blood supply entering the cartilage. Remember, cartilage has no blood supply at all. It's avascular, but there's processes, hormonal and other processes that are going to lead to blood vessels entering those cartilage bone, and that kicks off all these changes to happen. Okay. All right, so now those osteoblasts start doing their job and making bone tissue, right? They're sending out that osteoid stuff that contained calcium phosphate salts as well as the collagen, right? So it's going to make this bone collar around the outside. So like a thin layer of bone around the outside of that cartilage bone. And by doing that, it actually kind of cuts off those chondrocytes from a blood supply. Okay, there's like cartilage cells that are still in the middle there. And by putting this bone collar around the outside, that pretty much cuts them off from any nutrients. Okay, and then those start to die. Okay, and when those cartilage cells start to die, they leave a cavity on the inside, right? And that's what we have inside of our long bones, is a big cavity, right? There's that hole in the middle of our long bones, in the diaphysis. Okay, and then from there we get blood vessels that kind of bore their way into the bone. One called the primary ossification center, and then two called the secondary ossification center. The primary ossification center is right in the middle of the bone. Get blood vessels to kind of bore a hole through that bone collar, and then just start sending in a bunch of blood. Gonna get some osteoblasts from that, and then they're gonna start making bone. Okay, so the osteoclasts actually help that. They create that hole in the bone collar, right? And then that blood vessel comes in, and then we start ossifying from there. Same thing happens in the diaphyses too, in the ends of the bone. We break a hole through, send blood vessels in there, and start to develop bone. Okay, so now we get this process of breaking down most of the spongy bone to hollow out this medullary cavity. Okay, and then it starts to fill with bone marrow. The epiphyses start to finish the ossification process, so lots of osteoblasts sending out bony material. And then whatever calcified cartilage might be left will be broken down by osteoclasts and then replaced with bony tissue by the osteoblasts. Okay, and then the cartilage that's in those growth plates we were just talking about just stays there. It's the same cartilage that we started with as the whole bone, but now the only part left is that little line where that growth plate is. Okay, so that kind of walks you through the process a little bit. Now I want you to spend a little bit more time with it with your team via looking at this image. Okay, these 4 images, they're not in the correct order. Okay, so I want you to kind of figure out which one is which one is, put them in the right order, and then talk through what's happening in each one. Okay, and then I'll open it up on the clicker so you can send in 4 letters, and so send those in the correct order. Okay, go ahead, start walking through that. And then once you're done doing that, you can start kind of practicing this too, like we talked about, okay? Writing out that process. Give you a few minutes to do that.
Cartilage, just like those from cartilage, that continues to happen, and with that happening, the cartilage was starting to create that cavity in the middle. With that, there was a flux create more of in the middle in that cavity, create more bone tissue there. Then what's the thing as well, bone to the very end, where everything is filled, all this blood that's in the turns all itself, but it's and close.
So if you finish this part, then you can go to the next slide where you're kind of practicing writing out this process and drawing words like we talked about. By writing it out like that, you're kind of forcing yourself to summarize information, to process information, to work through it, right? And that's really how you learn it, right? You don't just learn it by just memorizing the slides, you learn it by having to process it. And a lot of people tell me when they study, they kind of talk through processes like this with each other, which I think is great. I think that's a good start, and I think that's something you can be doing now in class. But I do think it's important to kind of go to the next level and write it out, because then you can get a little bit more specificity, right? Because your friends don't always stop you and tell you, oh, you missed this one thing there, right? But I think talking it out is a good place to start, and then writing it out so you can compare it specifically to your notes is kind of a next step.
Yeah, it's, no, it's, I know, right?
So it creates the spongy bone, and then in the next step, just gets rid of that spongy bone. That's what
Talking about
it says.
in the cavity,
Like in the cavity, so it makes the spongy bone in the middle, and then it's like, okay, well, now you're there, I don't need you anymore.
All of that, yeah, pretty much.
Okay.
Kind of starts inside there.
So what's the point of the spongy bone?
Yeah, it just does like the whole thing. Kind of starting with the spongy bone and then for the bone marrow. It's probably not quite maybe specific amount. All right, I think we're almost there. Go ahead and I think there's maybe 3 more of you that haven't sent it in on your clicker, so just make sure you hit the send button. Good. Good. Okay. Looks like we pretty much got everybody there. Yeah, let's go ahead and come back together. I know you may not be quite done writing that out, but yeah, I think it's a good process, a good way to practice that. Yeah, let's go ahead and come back. So about 2/3 of you are saying the same thing, which is starting with B and then C and D and then A. Okay, so let's take a look at that real quick together here. Okay, so B is obviously the one that's still the most cartilage-like, right? It's almost all cartilage, but we can see this kind of transition point right here, right? Those blue cells are kind of supposed to be the cartilage cells, and then the yellowish or beigeish ones there are supposed to be the bone cells, right? So we can see that switch happening, right? We can see the membrane. This is kind of supposed to be the membrane, the cartilage membrane switching over to the bone membrane, right? From over to the periosteum. Okay. And then we can see these cartilage cells that are in the little lacuna there, right? Okay. So that's B. That's the first one, as you guys said. Okay. And then you guys said that C was the next one, right? So now we can see that we pretty much have a full intact bone collar. Okay. But now this is, what is this trying to show? What kind of cell is that? And why is it looking like that? Yeah. Calcified cartilage. It's like a dead cartilage cell pretty much, right? It's a cartilage cell that's been cut off from its nutrients by that bone collar. Okay, so it's still in that little lacuna, that little hole, right? But the cell itself has kind of shrunken and gone away because it doesn't have connection to the nutrients anymore. Okay, so we're going to start having a bunch of holes like that inside of the diaphysis of the bone. Okay, and then we go over to D next. You can see the primary ossification center there, right? And then we see the secondary ones here, as well as here in the epiphyses of the bone. So diaphysis in the middle, that's the primary site of ossification, and then the 2 secondary sites on the ends there, those epiphyses. Okay, and now we can see a full bony matrix kind of forming there with osteocytes that are there. Started as osteoblasts for sure, releasing that stuff. And then we have the role of the osteoclasts here, right? First of all, boring the hole in the calcified cartilage as well as that bony collar, so we can send in those big blood vessels. And then by sending in all that blood, that gives all the nutrients we need for those osteoblasts to do their job and lay down a bunch of new bony tissue there. Okay, and then finally we get over to A over here, step 4, where now the osteoclasts are working to break down some of that bone that was just laid, right? We put bone in there, but now we're hollowing out the inside of that cavity, and the rest of the calcified cartilage is being replaced by bone. And we can see that. And so all we have left here is cartilage in the growth plates, as well as on the articular surface, right? So that articular cartilage is also still the original hyaline cartilage that was there to begin with. Okay, we can see some osteocytes there, that have pretty much trapped themselves in by releasing, but they were osteoblasts, releasing that osteoid. Now they're osteocytes stuck in that little spot with all the stuff surrounding them that they released. Okay. What questions do we have on that process? Yeah, go ahead. Wes.
For number 4,
Yeah.
is it the top of the bone, the head, or is that still spongy tissue, or does that also hollow itself out?
You talking about in here?
Yeah.
Yeah, in here. Yeah, that doesn't hollow itself out. In our epiphyses, we have spongy bone on the inside. And that's typically going to be once that bone becomes an adult bone, that'll be the main place we have red bone marrow at that point, is
Okay.
within the spongy bone of those epiphyses. Yeah, and then we'll have yellow bone marrow in the middle in that cavity in the diaphysis. Yeah. Okay. Other questions? Okay. All right. Okay. Let's go ahead and answer this question here. Chat with the people on your team about it for a sec before you send it in. Take your guess, see what you think. All right, go ahead and send it in when you're ready. Give you about 10 more seconds. While I'm waiting for those, I would encourage you to do the extra studying you need to do this week. And a couple ways to do that would be, number 1, go to the Wednesday night review session at 8 o'clock, right? Another way would be sign up for my office hours. Or if you know one of your friends is coming, just come with them. It's not a big deal if they're individual appointments when you're just coming to ask questions about the test and go over material. So I've got office hours this afternoon, Wednesday afternoon, and then also mornings, Monday, Wednesday mornings as well. So take advantage of that. Love to help you be successful on the exam. So, okay, good. 91% of you are saying B. So bones adapt to external stresses by getting stronger or weaker, depending on the stress, right? If we don't stress our bone enough, it gets thinner, it gets weaker. If we put stress on the bone, then it gets thicker. Okay. All right. Okay, so let's talk a little bit about bone growth here. Okay, there's 2 primary types of bone growth. The first one, appositional growth, means when our bones get thicker. Okay, this is the only type of growth that adults have after the growth plates have closed. His bones can get thicker. Okay, and this is adding on those osteons to the outside of bone. Okay, so we're adding on more of those lamellae, right? More of those cylindrical, those overlapping cylinders. You're adding that on the outside, and as we do that, actually osteoclasts work to widen the medullary cavity a little bit as that bone gets thicker. Okay, and then we have elongation. This is growth at those epiphyseal plates. Okay, we'll see an image of it on the next slide, but you can kind of see the cartilage in that hyaline, or that hyaline cartilage in the growth plate. The bottom part of it is replaced by some bone. And then the top part of it, we're making new cartilage. And so it's kind of just chasing this cartilage line up as the bone lengthens. The cartilage is also growing until eventually that bone just overtakes the whole cartilage, and then it becomes bone. And then that's when growth stops. Okay. So yeah, pretty much looks, well, let me show you on this x-ray real quick first. If you've ever seen an x-ray on yourself when you were a kid before your growth plates have closed, or another time, that's what it looks like, right? That's the growth plate on a tibia, right? There's one on a fibula, okay? It's actually just separate bones, right? There's no bone connecting those things. It's cartilage and some ligaments that hold that together. But so a child x-ray is much harder to interpret than an adult x-ray because there's so much more going on. There's many more gaps, lots more joints is really what that is. Okay, so when we look at growth at the epiphyseal plate, this kind of shows it nicely. We got new cartilage forming up here, right? And then down here at the bottom, we see that cartilage is becoming bone, right? So we're adding bone to the bottom, okay? And then that cartilage is growing more on the top, but it just keeps kind of chasing it upwards And that's kind of shown by this image here as well. And that's really how growth of that epiphyseal plate occurs. Okay. And this is really controlled by hormones for the most part. Okay, so growth hormone is one of our primary ones that helps us do this. That's released by the anterior pituitary gland. We'll get into the endocrine system a lot more next semester, and we'll dive into all the anterior pituitary hormones, but that's just one of the important ones. Okay, and then testosterone in males or estrogen in females is very important for growth, as well as triggering the closure of those growth plates at some point. Okay, but these stimulate those chondrocytes to start the growth process, and then that's when different growth spurts can occur in kids along the way. Right, like my son Soren, he's almost 6'2" now at 14, and like just about, I mean, like a year and a half ago, he was probably 6 inches shorter than that, you know, or maybe even 8 inches shorter than that. He just shot up in an amazing way. It's just like amazing to see how fast kids can grow. I'm sure you guys all surprised your parents when you did that too, but it is just kind of a wild thing to watch, how much growth can happen in a very short period of time in kids. And then these sex hormones in males or females dictate some of those sex specific features, right? Some of the pelvic features in the skeleton that you guys looked at in the lab. Males typically have thicker bones, typically have thicker kind of foreheads and jaw lines. Those are specifically dictated by levels of testosterone and estrogen. And those sex hormones are again triggering the closing of those growth plates when growth stops. Okay, questions on any of this so far? Go ahead, Wesley here.
So you said like the pelvis, is it like when a boy baby is born, is the pelvis already thinner or not? Like,
yeah, you don't get
later
too
in
much of
life?
that. Yeah, you don't get too much of that till puberty. And then yeah, I mean there are some small differences, but they really become, you know, more distinct once puberty hits, because you don't have too big of differences in those sex hormones until puberty happens. Yeah. So, good question. Okay, bone remodeling. We've kind of been talking about this over the course of the past couple of classes, but it's this continuous process of breaking down bone and then rebuilding it, right? And again, responding to stress or lack of stress. One principle that applies to really all tissues in the body, but it also applies to bones, is a principle called the SAID principle. Okay, and it just means specific adaptation for imposed demand, right? So whatever demand we put, or whatever stress we put on a tissue of the body, that tissue is going to adapt itself very specifically to be able to withstand that stress better next time it receives that same stress, right? And bone this applies to bone too. It applies to cartilage. It applies to our muscles. Obviously, that's the one we typically think of. It applies to our skin, our ligaments, our tendons, our bone. All of those things adapt to the stresses that we put on them, which is one of the most amazing parts about the human body, right? I mean, we can create robots and other things that have all the right structures, but we can't create robots that heal themselves, that respond and grow and adapt to stressors, right? That's really one of the most incredible things about the body. This is a kind of this classic example, this classic study of tennis players where they did x-rays of the arm, their dominant arm, their serving arm, versus x-rays of the non-serving arm. And they just noticed that the radius and ulna in that serving arm were quite a bit thicker than the ones in the non-serving arm. This was kind of the first idea that was like, wow, bones actually adapt to the stresses we put on them. And we know they adapt in incredible ways, very specifically and very drastically as well. So, okay, questions about that at all? Okay. All right. The process of remodeling is driven by these two cells we've already talked about, right? Osteoblasts, which are there to help us thicken the bony matrix, right? And then osteoclasts, which are there to help us break down the bony matrix. Osteoclasts are full of very powerful enzymes in the little lysosomes inside of them that are going to help us break down that organic matrix, break down all those proteins, all that collagen, right? But then they also release very strong acids to degrade those calcium phosphate salts. Okay, and again, just like we've been saying, bones are the strongest where they receive the most stress. And really it's the balance between what's known as osteoclastic activity and osteoblastic activity, which is going to dictate how strong a bone gets, right? And if we have too much osteoclastic activity not followed up by enough of that osteoblastic activity, then bone starts to thin, okay? How many people have had a stress fracture before? Yeah, got a few? Yeah, wow, quite a few, yeah, from running, what kind of sports, ladies? Basketball, okay, which bone? Fibula. Oh, fibula, interesting. Yeah, what about you? What did you say? Preston too? Did you say too? Yeah, go ahead. Mm. Mhm. Sesamoid bones. Okay, interesting. Yeah, both unique ones. Yeah, fibula and sesamoid bones. Yeah. Any tibial stress fractures or metatarsal stress fractures? Yeah, those are probably the most common. Like fifth metatarsal is a really common one. Tibia can be somewhat common. But the deal with a stress fracture is when we do something like go out for a run, right? We go out for a run, that puts a lot of stress on our bone, right? But that stimulates our osteoclasts to actually break down some of that bony tissue. And then our osteoblasts come in and rebuild it back up a little bit stronger, right? That's kind of the normal process. But if we're in a situation where we put that stress on, osteoclasts are coming in and breaking down, and then before we give those cells enough time to really come in and do their work, we hit it again too hard with another stress, right? And we don't really give ourselves enough rest time. We hit it again with another stress, right? And so we never really can kind of transition back to that building back up phase. We're just in the kind of the breaking down phase, and the osteoclastic activity exceeds the osteoblastic activity, and bones just starts thinning in very specific spots, right? And that's really the cause of a stress fracture. So, yeah, other questions on that? Yeah, go ahead. How does it heal? Rest. Yeah, it's a big one. Yeah, rest. Because we gotta break up that cycle of just constant stress leading to the process of trying to break down. And so we can do that by resting for sure. And then the osteoclastic activity slows down and we can start give that bone time to build back up. But if we pushed ourselves into deep levels of stress and deep levels of what's called overtraining, then it can take months and months to actually kind of switch your body back to the kind of more of an anabolic state, which is like building things back up. So yeah. Hector, do you have a question too?
With regards to the healing, what does a bone stimulator do to the actual bone? That's what I have to do.
Okay. Yeah, it's the same kind of idea. That's like we want to put some stress on the bone because that does stimulate these cells to do their job. We don't want to put too much stress because the bone's already kind of weak. And if we put too much stress, then we're going to stimulate too much osteoclastic activity. If we put a little bit of stress, that'll activate some of the osteoblasts to kind of do their job and respond to that little bit of stress you're putting on with the bone stimulator and try to build it back up. So, yeah. Yeah, go ahead. Yeah, sometimes they show up on stress fractures can show up on x-rays if they're bad enough, but most of the time they don't. Most of the time you need something called a bone scan or an MRI to see it. Just looks like kind of like a little bit of like lighter spot in the bone. And yeah, so most of the time they can't. But the big concern is that and I've seen this multiple times where somebody has a stress fracture and they try to keep playing and then they get a full fracture, like their bone breaks because it was really weak in that spot, but yeah. Okay. All right, well, let's talk a little bit about homeostasis inside of bone of these calcium levels, right? We talked about calcium being really important for muscle function as well as heart function, nerve function. Okay, and we talked about how most of our calcium's in the bone, okay, 99% of it. And so we have when our blood experiences a decrease in calcium, right, our blood calcium levels go down, then we have a special hormone released it's called parathyroid hormone, released from what's called the parathyroid gland. And that directly stimulates our osteoclasts to do their job and start breaking down some bone. And then it inhibits the osteoblasts from doing their job because their job would be pulling calcium out of the blood and putting it into the bone, right? So we're activating those osteoclasts, inhibiting the osteoblasts, and that's going to be adding calcium to the blood. So that brings our blood calcium levels back up. Okay, just the opposite happens when it's the other way. Okay, if we have too much calcium in the blood, we have a separate hormone that helps us with that called calcitonin. Okay, calcitonin is released from the thyroid gland, which is right there by the parathyroid as well. that's going to do the opposite. That's going to activate our osteoblasts to do their job and pull calcium out of the blood, add it to bone, but then it's going to inhibit those osteoclasts so we don't break down more calcium and put it into the blood. Okay, so you can see those glands here right in the neck. The thyroid glands are the bigger pink ones, and the parathyroid are just these little small ones there. Okay. All right, so just a little bit of the endocrine control of our bones there. Okay, let's go ahead and do this one here real quick. All right, give you about 10 seconds to go ahead and send in your answer. All right, so the vast majority of you are putting D for this one. So when low blood calcium levels are detected, the endocrine system releases parathyroid hormone, which stimulates the osteoclast to break down bone and release calcium into the blood. Okay. All right, let's keep going. Okay, so we got 6 different fracture types here. And so you can see those there, right? So we got this shows like kind of a drawing of it and then an x-ray of it. So this is a spiral fracture, which kind of what it sounds like. It happens by twisting of bone in a forceful way, right? We got compression fractures, which happen from smashing down, landing from a fall, landing right on your feet or on your butt, is a common way for this to happen to the vertebrae, right? Especially in older people that have softer bones. Okay. A comminuted fracture is pretty much one of the nastiest fractures you can have. Is pretty much just like shattering of your bone, right? So it can be a major compressive forces, just smashing everything. You get multiple pieces, multiple chunks. A lot of times that requires some kind of surgical intervention to put everything back together. An avulsion fracture, we talked about avulsions with the skin. This is when a chunk of something gets pulled off the body. So it can be common, like right here, you have some ligaments that hold your tibia there to your talus, and sometimes the ligaments are stronger than the end of the bone there actually, and the ligament holds, but it rips the end of the bone off, right? And that's what an avulsion fracture is. Green stick fracture is really common in kids, where it's kind of like if you've ever pulled a twig off of a tree that's still very alive, and you try to bend it, the top part typically will stay intact, but then maybe the bottom part kind of buckles. That's what bones do in kids as well, because there's such a higher level of collagen in them, and they're not as hard. And then a epiphyseal plate fracture, a growth plate fracture, right, is when there's some kind of shifting of the bone on one side of the plate versus the other. Okay, couple quick ones here. See what you guys think on this one. Let's do a little diagnosis, get to be a radiologist for a second. Gonna be a number. This is from the Sawyer family. It's a Sawyer x-ray. Yeah, that's Soren's ankle when he was, how old was he? I don't know. I think he was 8 or 9. All right, go ahead and take your vote there. Send it in. Give you about 10 seconds. Yeah, make sure you hit send with this type of question. Got a few more of you. Pretty good mix between 5 and 6 there. Okay, so who wants to raise their hand and show me where they saw the avulsion? Go ahead, Alexia. Right there? Yeah, good catch. That's not an easy one to see. Yeah, that's exactly what it is. He had an avulsion fracture there, where that ligament it's called the calcaneofibular ligament, connects from the fibula to the calcaneus, ripped a chunk of bone off instead of the ligament tearing itself. But then who saw the growth plate fracture that wants to show us where that one is? Wesley?
Not on the thin bone, just up, because it looks like it's kind of just shifted.
Right there, right?
Yeah.
Yeah, exactly. Yep. Had a growth plate fracture too. So you guys are both right. Yeah. Had both. Yep. Bulging fracture and epiphyseal plate fracture. Yeah, you can see it's kind of just like shifted in like that. If they're bad enough, then the doctor has to set them, right? If it's just a little bit off like that, then it'll usually find its way back on its own. So, okay. Questions on that one? Go ahead. Falling off a curb in a parking lot. Excited for sure. Yeah. Okay, one more here. Let's do this one. All right, go ahead and hit send there. Send something in, give you about 10 seconds. All right, so about 80% of you are saying 3 there, the green stick fracture. And this is a really nice x-ray of one. This is not one of my kids. This is just one I found online, but yeah, you can see it there. You can see this side is definitely like all the way open, right? Like it's cracked, but then you can see it's really completely intact on that side, right? And that's really what those green stick fractures look like. So, okay, questions about any of these? Yeah, go ahead, Julia.
So for something like that, we just put it in a cast film. and
You
just-
do still cast it, yeah.
just like readjust it.
Yeah, most of the time it just readjusts on its own. Yeah, in this case, there's really never much displacement since it's still attached. So yeah, they just cast it so it can kind of make its way back. Yeah. Yeah, other questions? Yeah. Yeah, good question. If that's the radius of the ulna. I think that's the radius, but yeah, I'm not sure. How many of you guys thought it was the radius? You don't have to say that just because I did, but yeah, could be the ulna too. I have to take a little bit closer look at the whole thing, but yeah, I'm thinking that's the radius. Looks like the ulna gets a lot thicker proximally. It looks like that's the proximal part of the ulna, but not 100% sure. Yeah, it's a good question. Okay, all right, let's talk a little bit about the fracture healing process here. And so when a bone breaks, as we've talked about, there's lots of blood in there, right? And so we get a big blood clot. That's the first step, right? This big blood clot inside the fracture. Okay. And one of the cool things about our blood is it contains a lot of materials that we need for the healing to happen already. So wherever that blood ends up, we've already got some special proteins there that are going to help stimulate this whole process. Okay. As well as special cells like phagocytic cells. Okay. So we go from the blood clot to this kind of cleanup phase where we get fibroblasts that are landing there, chondroblasts, and those chondroblasts are then sending out collagen-like tissue, sending out cartilage-like tissue, same thing that the fibroblasts are doing. Blood vessels start to regrow, okay? And so we get what's called this kind of soft callus, okay? So it's like a cartilage callus, right? So we can see that there. Soft callus is the next step. And then the collagen actually will span the full gap of the crack in the bone. And there's actually I don't have it here on the slide, but there's other little proteins inside there called actin and myosin, which are motor proteins, which actually will kind of span the gap and help pull that bone back together a little bit, which is kind of a cool part of the process. And then we go from there to what's called the bony callus, right? So it looks a lot like spongy bone. Okay, it's very similar, but it goes through the whole thing, right? It's on the outsides where the compact bone's supposed to be, and it's also on the inside where there's supposed to be a cavity, right? So we get this full kind of bony callus there. This is what we see at about 8 weeks. Okay. How many people have had a cast within the past couple of years? Broken bone, cast, yeah. How long do you have to leave that cast on for, Cameron? Oh, compound fracture, which bone? Oh, your humerus. Ouch, that's a bad one. Yeah, yeah, yeah. What about you, Riley? Did you have your hand raised too? Oh, you're just nice. Gotcha, there you go. That's the quickest fracture healing I've ever heard of, 20 minutes. Yeah. But yeah, so it's typically now about 4 to 6, sometimes 8 weeks for a cast. And so you can see that corresponds with the formation of this bony callus, right? So when you take that cast off, your bone doesn't look like it did before you broke it, right? It's in this state of this bony callus. It's not in its final state. Okay. So it's still pretty strong, it's nice and strong because it's bone all the way throughout, but it's not a fully healed bone yet. Right. And then to get all the way to this remodeled state where we get compact bone back on the outsides, we get our cavity back there again. That's like several months, maybe 3 to 4 to 5 months, depending on which bone we're talking about. Okay. Other questions on that? Go ahead.
And at least say that like when you break a bone, once it's healed, it's stronger at that point of the bone. Is that like just because it's newer bone, or like what makes it so it's usually you don't break it in the exact same spot?
Yeah. I think it actually is a little bit thicker there. Kind of, it's almost like a scar in bone, is like it actually becomes like a little bit thicker in that spot compared to the other spots. Yeah. Oh, good question. Okay. All right. And then this idea of like I've been talking about, this balance between osteoblastic and osteoclastic activity, again, is really dictating the strength of bone. You don't need to memorize all of these little factors here, but I will highlight a couple that are important. Okay. So this whole side is looking at factors that increase bone being deposited, right? That we get more laying down of bone. Whereas this is the opposite, increasing bone resorption, which means like pulling calcium out of bone, thinning bone. Okay. So a couple of the big things that I'll mention here are some vitamins, right? You need certain vitamin intake. Vitamin D is definitely one of the most important ones, as well as calcium, right? So calcium, vitamin D, very, very important. And then this one here is a big one too. Are we putting any load on our bone, right? So weight bearing activity is one of the most important things for people as they age, because that's what keeps stimulating their bone, keeps making your bone thicker and stronger. You need to do weight bearing activity, or resistance training is helpful too. So that's kind of that one. And then in females, estrogen is very important. And so this is why postmenopausal women tend to be much more prone to osteoporosis, because their estrogen levels have dropped quite a bit at that point. We'll talk about that in 1 second. But yeah, those are kind of the big ones. I wanted to highlight the calcium, vitamin D, and then just weight bearing activity, very important for thickening and strengthening bone. Okay, so osteoporosis is again, this breakdown's happening faster than deposit. Okay, but yeah, so then we have a high likelihood of an actual fracture, right? So increased fracture rate. Vertebrae, neck of the femur, the common ones, like when you hear about like grandma broke her hip, it's always that spot where the femur comes up like this, and then you got the head right there. It's that neck of the femur is a very typical spot to break the hip, right? The only way this is different from a stress fracture is in osteoporosis, it's really like the whole bone that thins, right? Whereas a stress fracture is one specific spot where that stress was. Okay. Yeah, and so the risk factors, again, postmenopausal women, due to that decrease in estrogen, age. So 70% of women have it by the time they reach the age of 80. So that's a lot, right? A high percentage. Okay. Low calcium intake, sedentary, not getting any exercise. You can help it with calcium and vitamin D, like I talked about, exercising, like I talked about. And then there is some possibility of hormone replacement therapy after menopause, but there's also lots of side effects with estrogen replacement. And so it's not fully necessarily recommended for everybody to do that. Questions on this? Go ahead, Hannah. It's not just with women, just a much higher likelihood in women, much higher prevalence of osteoporosis in women versus men, but men can have osteoporosis as well. Yeah. Yeah, and then lastly, osteomalacia is a little bit different. This is softening of bones, typically due to lack of vitamin D, can be lack of calcium. And this is when bones kind of bend and bow. This is what's known as rickets when children have this due to a lack of vitamin D intake, somewhat common in developing countries. So, all right, guys, we're all done. We'll see you on Wednesday.
Thank you.
See you, Jasmine. Bye.
Bye.